So yeah, that's how you calculate delta H from Lewis structures and that sort of thing. Okay. The next section talks about VSEPR. VSEPR is a very big topic. It stands for valence shell pair electron repulsion. Valence shell electron pair, it's actually, VSEPR. So it's like a kind of almost like Viper or something. It has a weird pronunciation. So this is valence shell electron pair repulsion theory, and it's just one theory, and it basically states that electrons repel. Okay. They like to be far apart as possible. And that's why molecules have different shapes or geometries. And we're talking about a 3D shape or a three-dimensional geometry. Okay? So the easiest thing is that there's a lot of observations here that have been made. X-ray crystallography, microwave radiation spectroscopy, and other tools to figure out what the shape of molecules are. Okay? And BeF2 is found to be linear. Okay? And the idea is that this fluorine has a whole bunch of electrons, this fluorine has a whole bunch of electrons. Technically, it's these electrons that make up the bond and these electrons that make up a bond that want to position themselves as far away as possible on opposite sides of the beryllium atom, giving you an angle of 180 degrees. Okay, so that in a nutshell is valence shell electron pair repulsion theory. Okay, now if you have your central atom, okay, the central atom is called E in this book. Everybody uses a different okay, so these are some definitions. Okay, it's in the book as well if you read through it all. But the central atom is called E. And then bonded atoms are X. Okay. And unshared electron pairs are just called dots in your book, I guess. Dots. I call them U. Your book is not the best here, but so this right here has the general form EX2. Okay, where you have a central atom bonded to two atoms. All right. Another example would be carbon dioxide. Carbon dioxide we're familiar with is CO2. We've already drawn the Lewis structure of this many times. This is the E, all right? Each of your oxygen atoms are X, all right? And there's no lone pairs on the central carbon. This also has the general formula EX2, or a central atom E bonded to two atoms X. Now, it is technically bonded by a double bond, but it doesn't matter, okay? X is a group or atom. All right, it's just an atom. And so another example would be acetylene. All right, let's focus in on this one right here, okay? This is your central atom E. It's bonded to X, which is just, I don't know, a side group, right? And then also this E is bonded to, yeah, it's triply bonded, but don't worry about that. It's bonded to this whole thing, which is just X, all right? So this also is called a linear molecule. The bond angle between this bond and, you know, this bond on the right would be 180 degrees or linear, okay? So again, that's just the very basics of this, okay? Okay, so for figure 7.16, it's summarizing the different spatial arrangements you can have for a central atom surrounded by bonded groups. And this table is with 0 lone pairs on the central atom. So another thing you'll notice is that they're being very lazy with the Lewis structures. They're not drawing any lone pairs on any of the surrounding atoms because that does not influence the geometry of the central atom. So an example of just a linear molecule would be this guy here, and I just want to, let me just highlight it. We call this linear. That means in a line. And we have a central atom that's bonded to 3 groups. So for example, BH3 is boron bonded to 3 groups. And it looks like this. There's a 120 degrees angle between all of the 2 hydrogens, and that's the furthest away you can possibly get 3 groups. But it is in a plane. It's still planar. Now, you get to a complicated molecule here where you have 4 regions of electron density around a central atom. And here we have just 4 hydrogens here surrounding the carbon. And we call this tetrahedral. Okay, tetrahedral. If you look up tetrahedron, it's one of the 4 platonics. It's one of the platonic solids. Okay, and so it has an interesting geometry. If you have a wedge, that means it's coming towards you. Like 3D, put on your 3D goggles and pretend like that's coming towards you. And a dash. So a wedge looks like this, and a dash looks like this. So a dash means it's going behind. Here's methane. The carbon is black and the hydrogens are white. It's a CH4 molecule, and it's not in a plane. Now the angle between these any 3 atoms is 109.5 degrees, okay? And let's talk about the wedges and dashes here. So if I position it so that this hydrogen and this carbon and this hydrogen are in the plane, you will see that this hydrogen here comes out towards us. That would be represented as a wedge. And this hydrogen going away behind us is represented as a dash. Okay? So that's what we are trying to illustrate here by drawing a 3-dimensional space. Okay? The wedge hydrogen means it's coming towards you, and the dash hydrogen away. And things get more complicated when you get to higher amounts of electron density. PF5, for example, is something called trigonal bipyramid. Okay, and you have several different bond angles. You have 120 degrees between the 3 fluorines here that form up the triangle part. So that's the trigonal part of the molecule, and it's a bipyramid because you have a face coming up to the top, and you have a face coming down to the bottom. So it looks like that weird 6-sided die from Dungeons and Dragons. Maybe I shouldn't even draw that, okay? So that's called trigonal bipyramid. And octahedral is when you have 6 things surrounding a central atom. So SF6 is an example of that. We call that octahedral. And they have 2 different bond angles, 90 degrees for the 4 in the kind of the middle, and then 180 degrees from the 2 fluorines on the top and the bottom, or this fluorine and that fluorine, for example. So I don't know why they didn't put 180 in the figure. I think it's a mistake for their book. All right. So that's a little bit about that. All right. Now, once again, we are talking about molecular geometries. Okay. So 2 things, we call it linear. 3 things, we call it trigonal planar. 4 things, we call it tetrahedral. Okay, 5 things, we call it trigonal bipyramid. 6 things, octahedral. Okay, and you do need to memorize these things. There's not a table that gives you all these answers or something, okay? Now, the electron pairs also count as a group that repels another thing. So we want to discuss what do lone pairs do to molecular geometries. So lone pairs are a source of electron density that want to be away from other electrons in a molecule. So we want to look at the molecule NH3, okay? We have electrons that are lone pairs on the nitrogen, and we have electrons that make up the nitrogen-hydrogen bond. And all 4 of these pairs repel one another to position themselves approximately 109.5 degrees away from each other, okay? All angles here are going to be 109.5. That's the angle for a tetrahedron, okay? Now, what does the molecule look like? It looks like this because lone pairs are invisible. They don't show up as a shadow, for example, in X-ray crystallography or other kind of techniques. So the real molecule looks a little bit different, and it looks like a trigonal pyramid, okay, trigonal pyramid. The name is located right here. I hope you can see it on the video, trigonal pyramid, okay? Let me show you what this looks like with these cool little molecular models. This is why I wanted to go into organic chemistry, because you make cool models of things, and I said, wow, I really like playing around with this kind of stuff. I want to, learn more about it. So here's ammonia, okay? Nitrogen actually has 4 things attached to it. It has a lone pair, which is this stick sticking up. It's got 3 hydrogens, okay? So that's ammonia, NH3. But what we want to do is pretend like, those drawings that look like balloons? We want to pretend like we have a needle and pop that, okay? And I'm pretty sure I can't pop this off with one hand. All right, I did it. So now the molecule has this weird shape. It's not planar, okay? It looks like it's planar if I hold it this way, but it's not flat, okay? It's not flat. It's like a trigonal pyramid. So pretend like you're taking a picture of somebody, and this is your tripod, okay? So it forms a triangle, but it has a shape that pokes up into the sky like a pyramid, okay? So that's called trigonal pyramid. So NH3 is a trigonal pyramid, okay? Now, the actual angle here is not 109.5. It's actually about 107 degrees. Now, the reason for that is because lone pairs have a greater repulsion, okay? Lone pairs need more space. All right. Another classic molecule that is usually shown is water. Water is, of course, H2O. It has this Lewis structure. And we normally draw it bent. Okay, bent. It's not linear. Why? Because there are 4 groups attached. Okay, there's a lone pair there. There's a lone pair on this oxygen. There's a bonding pair on this oxygen, okay? And there's a bonding pair on this oxygen, okay? And we have 4 things attached. 4 things is called tetrahedral, okay? But grab your needle, pop this balloon, grab a needle, pop this balloon. What is the position of these 2 hydrogen atoms? Well, they're bent, okay? When you look at this molecule, it has the designation bent. If your central atom is E, and your bonded groups are X, and if your pairs are called U, okay, there's one U there and there's one U there. U stands for unshared electron pairs. This would be EX2U2, okay? So any formula that falls into that category with 2 lone pairs, 2 groups, is going to be bent, okay? It's bent. I didn't say what this one was, But if this is your E, okay, your hydrogen is your X, your surrounded atoms, and if this is an unshared pair, this is EX3U. So that's going to be trigonal pyramid, okay, trigonal pyramid. Okay, the easiest way to think about that is just pop that invisible balloon. Those electrons are, really small, hard to see. You can see a proton from a hydrogen atom. Okay, so that's H2O. All right, that's H2O. In figure 7.19 in your OpenStax chemistry textbook, it gives you now a more complete picture of the molecular geometries. Okay, so here we're talking still about molecular geometry. Okay. Now, we've talked already about what these molecules look like when they have 0 lone pairs. Okay, they have simple names. If you have 2 things attached, it's called linear, and we called that having a basic designation of EX2. That's not going to show up. EX2. We talked about trigonal planar. All right, trigonal planar, and that's going to be EX3. And we talked about tetrahedral. That's going to be EX4. Okay. We talked about trigonal bipyramid. That's EX5. And this one here with 6 groups is, of course, EX6. But it's called octahedral. I know 8 means oct, but it's because of the faces, and that's off the screen. Okay. Now, we now have begun talking about the influence of lone pairs. When you have lone pairs on the central atom, these electrons twist or bend the shape a little bit more. Okay. If you have something EX2 with an unshared electron pair, so U is that unshared electron pair, it's going to be bent. I like the word bent. It's smaller, shorter, easier to write. It sounds less technical. If you have something like this, like ammonia we talked about, that's going to have something that's going to have the geometry trigonal pyramid. And we talked about water. Okay, water has a bent structure as well, and that's EX2U2. So an example of that is water. An example of this is NH3. Okay, and we already did examples on the first column. Now you have crazy things over here, and there's only 1 or 2 molecules with these interesting names. So you have a seesaw-shaped molecule and T-shaped. There's only 1 or 2 molecules that even fall into that. Linear, quite a few of those. And then down here you have a square pyramid, square planar, and some other weird names. Okay, so linear there as well. Okay, so you have different molecular geometries depending on how many lone pairs you can possibly have contorting the molecule. Okay, so basically to figure out what the molecular structure is, you want to write the Lewis structure of the molecule or polyatomic ion, and you want to count the number of regions of electron density, such as lone pairs and bonds around the central atom. You have a single, a double, or triple bonds count as 1 region. And then you want to identify the electron pair geometry. All right. And then you want to use the number of lone pairs to determine the molecular structure. Okay. So these right here are called electron pair geometries. Okay. And then these over here are called, well, they're also called molecular geometries if you don't have any lone pairs. I just want to highlight what the book is saying. And then over here, these are all molecular geometries, okay? So that's how you do this, okay? So let's look at using that table. This is example 711. So we want to write the electron pair geometry and the molecular geometry for each of the following. So we have carbon dioxide, okay? So we write out carbon dioxide, okay? And step 2 is to figure out the electron pair geometry. So carbon here is your central atom, okay? And we have one group right here. We are basically looking at the atom. It's bonded to one atom called oxygen. We don't care about how many dots are on that oxygen. Okay, so it's one group. And remember, we call that group X. Over here, we have one group called X. And the central atom is called E. And on the central atom, there is no lone pairs. Now, the reason I'm making a big stink of this is because a lot of students, they count lone pairs way over here. Well, there's all these lone pairs. That's going to make it, you know, this weird shape. No, we count how many lone pairs are on the central atom, okay? So this is EX2. How do you position those two things far apart away from each other? It's going to be linear, okay? So the electron pair geometry is linear, okay? We're basically looking at this table, and we are looking at, let me use red here. We're basically looking at this, okay? And then there are no lone pairs, so there's the molecular geometry is the electron pair geometry. So that's the electron pair geometry, which is called linear, and that's also the molecular geometry. The next one we have is boron trichloride. So boron is in group 3, so it has 3 dots, right? Chlorine is in group 7, so we have 7 dots. 7 dots over here, and then we connect some lines to make the bonds, and we stop. Boron is a rule breaker. It's bizarre, and so that's the structure, okay? That's the Lewis structure. Now, we want to count different things here and so on. So boron is my central atom, so that's going to be called E, all right? And then each one of these guys here is a group. It doesn't matter that chlorine has all these lone pairs. It's bonded, right? We're just counting lines here. It's bonded to 3 electron groups, and it has no lone pairs, okay? No lone pairs on the central atom. So 3 groups, let me finish the designation here. It's going to be EX3. There's no U. There's no unshared pairs on the boron. So this is 3 groups. That means that it's going to be, we basically go back to here. Let me use red. If it has 3 groups, we call it trigonal planar. And it has no lone pairs, so the molecular geometry is also trigonal planar. Okay? So we would say the electron geometry is equal to the molecular geometry, which is trigonal planar. Okay? Check your learning. So we're supposed to do carbonate now. Now, carbonate, we've drawn this structure before in the earlier part of this lecture, so I'm just going to slap it up here to save some time. We can just look at one resonance structure. So let's just draw this one here, and let's analyze this, okay? So here's the central atom, okay? And it's bonded to 1, 2, 3 groups, okay? And there's no unshared pairs, and we know that this is called trigonal planar, okay? So the electron geometry and the molecular geometry is the same. It's trigonal planar, okay? So that's a little bit about that. And so let's review water. Water is this molecule here, as we very well know, okay? And this oxygen is bonded to one group, one electron pair group there, one unshared electron pair, and another electron share. Okay, so this has 4 electron groups. Okay, remember, a group can be a bond to a hydrogen, or it can be just a lone pair. Sometimes we draw a line to a lone pair. I kind of like how the book does that. So 4 electron groups is going to tell us, because you're counting the electrons, it's called the electronic geometry. Okay, and that's tetrahedral, right? Tetrahedral. If you could view the electrons, it would be a tetrahedral geometry. Now what we do is we take a needle and we pretend like these are balloons and we pop those two. What is the molecule going to look like? Well, we pretend like the electrons are invisible, and the molecular geometry is going to be called bent. Let's go back to the table and make sure we can see that, okay? So we found 4 things attached. So that was a tetrahedral electronic geometry for the H2O molecule. And we saw that there was the H2 molecule had 2 lone pairs, so it's bent. Okay, it's bent. All right. So let's do another one. Okay. Now, some of these molecules can be pretty weird looking. There's 2 different possibilities oftentimes for how you can do things. But let's do XEF2. Okay, XEF2. So step 1 is to draw the Lewis structure. So we set up our skeleton. Xenon is in group 8, so we need 8 valence electrons to get us started. Fluorine is in group 7, so we need 7 valence electrons to get us started. 7 over here as well. Make a line, which is a bond. Okay, and then count your pairs. There's 1, 2, 3, 4, 5. Okay, so there's 5 total groups. 5 total groups means, let's go back and look at the table if you're confused about the names of the basic groups. 5 total groups is called trigonal bipyramid. Okay, so trigonal bipyramid is when your central atom is bonded to 5 total electron groups. So that's an electron geometry. Of trigonal bipyramid. Okay, and now this is pretty far down in the table. This is my cutoff for where you need to memorize things. Let me make this really maybe bold. Yeah. All right. So let me highlight the section that you should memorize. Okay, you should memorize the basic geometries for 2, 3, 4, 5, and 6 for this column here. And you should memorize bent molecules, trigonal bipyramid, and bent molecules. Okay, and okay, so within the purple mark, learn these, all right? Now, XEF2, we said, was a molecule that had 2 5 total electron groups. So this is something that we should memorize. We should call it a trigonal bipyramid, okay? But you might not know, well, which one is it, right? Like, so for example, when you have 2 xenon atoms and 3 unshared electron pairs, that turns out to be linear. So the molecular geometry is linear, okay? Okay, and you might have thought maybe it would be bent or something like that, all right? So, which is a hypothesis. Let's do another one, XEF4. Okay, so XEF4, step 1, draw the Lewis structure. This is why it's very important to be able to draw Lewis structures. It's the first step in figuring out all the other answers. 8, 7, 7, 7, 7, draw a bond, draw a bond, count groups. So there's 1, 2, 3, 4, 5, 6. So you should know that 6 groups. The electronic geometry of this weird molecule is something we affectionately refer to as octahedral. Okay. You don't need to know this part, but if you go back to the table and you look, it's outside of the purple box, but this actually has a molecular geometry of square planar. Okay, square planar. Now, let's talk about large molecules, okay? So don't freak out on me here. Let's consider large molecules, okay? And what do we got here? Looks like glycine. So we have a protein. Okay, and this question might be phrased in different ways. What is the molecular geometry? What is the electronic geometry? Or what is the bond angle? Now, this is not a protractor question. So, for example, if I asked, what is this bond angle? Some students would say 90, because it looks like it's 90 degrees. Well, what you need to do is count bonds and then figure out what the electronic geometry is and think back to what we've learned, okay? So, for example, this is what we do. We count groups. Four means tetrahedral. Which means that it has an angle of 109.5 degrees. Okay? Let's do another one. What if we were asked to identify, okay, what is this bond between the oxygen, carbon, oxygen? Okay, what's that bond? Angle, you know, is it 120, 90, 180? What is it supposed to be? What is it? All right, so again, what you do is you look at this as the central atom and you count groups. Now here I'm going to slow down a little bit in case I lost you. When you count groups to this carbon, this is one group. This is one group. Okay, because there's a line going that way. And here's a line. This is one whole big old group. Okay? So we say that that carbon has 3 groups. Okay? 3 groups means, let me think, right? It means you have a trigonal planar geometry. Okay. How about this part of the molecule? I can't really highlight on black. Let's see. I'll highlight with white then. So how about this part of the molecule right here? Okay, the nitrogen. What is the geometry, molecular geometry of that nitrogen? If you look, we have a hydrogen, and then we have a humongous part of the molecule that way in a lone pair. And so if you look at this, this looks just like ammonia. It's trigonal pyramid. Trigonal pyramidal or trigonal pyramid, okay? So it's got 3 groups and 1 lone pair, so that's just like ammonia, okay? How about the oxygen right here? Well, that oxygen looks just like water, so we would say that's bent, okay, bent. And here we're talking about molecular geometries, okay, molecular geometries. All right, so if you see really big molecules, don't freak out. One of the questions I will ask you about is aspirin. Aspirin has this Lewis structure. We always do this one last when people have a headache and they're thinking, wow, I need to get some aspirin. Oops. So you might be asked, what is the geometry about that carbon, about this oxygen, maybe about this carbon, something like that. You might be asked, what is the bond angle here? What is the bond angle here? Okay. What's the bond angle here? Etc. Okay. And when you're asked for bond angles, you give the idealized bond angles. The idealized bond angles are in that table way back in the beginning, okay? So the important thing to think about is the polarity, okay? Polarity is mentioned ever so briefly in this general chemistry textbook, but it's a humongous part of future classes if you go on to take organic chemistry.